Hello, this is Rob Stewart speaking. I've recorded this in Houston, Texas, and my apologies for not being able to present this in person. But I've broken an ankle and am not able to travel. I hope that the Athens meeting is turning out very well. This work is from a PhD student, Craig Hyslop, at the University of Houston, and myself, Rob Stewart. And we're going to be talking about using ground roll, reflected surface waves, to create images of the subsurface. We'll talk a little bit about that and why we're motivated to use ground roll, and then some about Rayleigh waves and the reflections. Then we'll be informed by how we process VSP data, vertical seismic profile data, for ground roll, and then look at how we can use 3D recordings of ground roll to use migration type processes to make pictures. So again, we're motivated to use ground roll really to find subvertical features, faults, discontinuities in the near surface, and other heterogeneities. Reflection seismic is a great measurement, but it's not perfectly suited for vertical features. It makes excellent images of sub-horizontal or more horizontal features, but vertical features it struggles with more. So what we will use ground roll for is, of course, in the classic way to determine velocity and ultimately statics, but also to use the scattered or the reflected ground roll, the backscattered ground roll, to make pictures on their own. So just a little background, remember that ground roll is, in the simple case, retrograde elliptical as it propagates with velocity close to that of shear waves. And we can use the dispersion curves when we decompose the ground roll, use dispersion curves to get velocity with depth. And there are certain sensitivities as seen in the graph, that as depth increases, we have lessening displacement. Low frequencies are still sensing deeper areas, and high frequencies are seeing the near surface. And we've been using that for many years, and they're great packages and great papers on how to extract dispersion curves and shear wave velocities from them. Less has been done on ground roll scattering and the reflections of ground roll from interfaces or discontinuities or heterogeneities. So we're going to be thinking about how we can use backscattered or back reflected ground roll to make pictures. Now, we first observed this in the lab, and I'm showing some experiments that we've undertaken at the University of Houston. And in the upper left-hand corner, you can see a block of plexiglass and blocks of aluminum and an ultrasonic transducer. Transducers measuring typically at 0.5 megahertz or 1 megahertz, 10 to the 6 cycles per second. And just below it, you can see a shot gather. And the shot gather in the plexiglass, we can see the lower velocities of the direct arriving P waves, and then the velocity of the ground roll. Now the ground roll hits the interface and transmits, but as well the ground roll reflects. And it's that reflecting ground roll that interests us. Now, can we actually see this in the real world? And we've done some experiments in the area around Houston, in fact near one of the big shopping malls. And in this case, once again, you can see the ground roll propagating outward, hitting an interface of some kind, and scattering back. So how could we use that backscatter to actually find faults or find heterogeneities in the near surface? And we can do that by being informed with VSP. But let's first look at some synthetic data. Now the model is in the upper left, and we have a low velocity layer on top of a 300 meters per second half space, and then a block of heterogeneity at 400 meters per second. And using a forward model, of spectral element forward model, we can generate the full elastic wave field. And in particular, you can see ground roll propagating down, dispersing, and then reflecting back from this model. Now, if we first of all extract just the first mode dispersion curve, then we can find the ground roll velocity as well as extract a shear wave velocity from that. and that shear wave velocity extracted from the direct arrival, or the outgoing wave, will provide us a basic first cut, or first approximation at the velocity. So in this sequence of processing steps, in number one, we've got our synthetic data, outgoing ground roll, the reflected ground roll. We flatten on the ground roll and basically de-disperse it or deconvolve it. Then we run a filter across that to enhance it. Then we subtract the enhanced outgoing from the flattened data, leaving the residual. You can see the residual here. And this emphasizes, similar to VSP processing, this emphasizes our scattered wave. Then we can enhance that and actually back propagate it and mute it, and then deconvolve it with the enhanced outgoing wave. So we'll do another deconvolution. Then from this we can look at the spectrum, and the spectrum in frequency and position gives us our first type of picture. So finally, after all this processing, we've got offset and frequency. Now what we're going to do is we're going to assume that frequency dividing into velocity gives us wavelength, and wavelength we will map to depth. And so that's an assumption, that's an approximation, that each frequency, when we know its velocity, can be mapped to a depth. So we take the amplitude at that frequency and map it directly to depth, and this is how we produce our image. So we've got x offset position and now depth and the amplitude of the scatterer, and this starts to provide us with our picture. And that's how we can make a picture from the scattered ground roll. So that's in the lab, and it looks very promising, and we've done that with a number of cases. Now let's go to the field and see if we can find this kind of energy and make an image of this in the field. So here's the area. This is one of the big shopping malls in the metropolitan region, and there's a major fault that goes right by the shopping mall, and we've acquired seismic data across this fault. So the red dots are a seismic line. The faulted area goes just on the east side of the shopping mall. Again, these data were acquired with a vertical vibrator. We used 3-component geophones. We're going to process the vertical component. Shot and receiver intervals were both 5 meters, and we shot on the half station. So we can first of all process the reflection data, and we've done that. And in the reflection data, we can actually see a number of faults. And these faults actually express and even break the freeway, and we can see that quite clearly on the roads. So we make our reflection image, and then next we process the data as was shown previously. We take our ground roll, go through the VSP-type processing, enhance the back reflections or the reflections, the back scatter, and make an amplitude and map that to depth. And in these bright colors you can see the reflectivity or the amplitude of the reflection, and we find that that maps reasonably well with the discontinuities in the reflection image and our known locations of faults from breaks in the highway. So that gives us an idea of how we can use this in a 2D sense. Now let's move into 3D. And our basic concept in 3D, and now we're going to look in plan view. And in plan view, we've got a shot and some receivers, and you can see the synthetic data, somewhat of a split spread here with the ground roll going and scattering from the discontinuity. In cross section, we can see our low velocity in the near surface, and then the vertical fault. Now, when we simulate waves, we can take our shot. We've got the waves emanating out from the shot, hitting the anomaly, the anomalous area, the heterogeneous area, going a bit faster. Then in the split spread, we can see the scattered ground roll. So now we want to migrate this scattered ground roll Now, there are a number of different ways to do the migration. We've used a STOFA algorithm, one-way split step phase shift migration. So we process the data for dispersion, then we deconvolve the backscatter with the incoming and create an image. So once again, here's our original outgoing wave field, the backscattered image, the decon, and that's how we do the imaging. Now let's also, that was synthetic data, let's look at some physical modeling data. We typically go from numerical to physical modeling data to field data. So we use our ultrasonic sources again and very small receivers, pin transducers. And once again, at an oblique angle, instead of going 90 degrees, we're going to shoot a line oblique to the interface. So we can see in the physical modeling data our first breaks, the ground roll, and then the scattered offline ground roll. Here's just a schematic diagram of that. And once we undertake the migration through the previous process, we can see that it's beginning to form an image. This is just the image from one shot migration. So now let's go directly out to the field, and these are some multi-component 3D data from the Marcellus Shale, an area of enormous activity right now, pursuing hydraulic fracturing and shale gas. This is the Bradford 3D 3C survey provided to us by Geokinetics and GeoPursuit, and thanks to them. You can see the recording parameters, and we're just going to select a couple of shot gathers and then process that. So we've taken a single shot and a line, and now we're going to migrate the data in 3D from this line. So first we'll take a look at the actual field data. Here's our outgoing surface wave, and for example, we begin to see what we interpret as reflected surface waves coming into the spread. There might be other events in here. It's a bit of a complicated near surface. So we're going to take a number of shots into this line and migrate all of those shots, process all of those shots. And when we do that, we find that we're getting backscatter from an area offline, and we're making a picture of that. These are the areas of reflections, and so we're going to interpret that as an area of heterogeneity. And we could do that for the whole survey. I'm just showing the one overlay at this stage, and we find that in fact that does correspond to topography. So our interpretation is that this backscattered ground roll is actually being scattered from topography. So just summarizing our work here, the near surface is very important for a number of ways, and we're looking to locate faults, especially blind faults that are not expressed on the surface itself. We want to locate anomalies and of course build a more detailed heterogeneous structure of the near surface for further processing. The ground roll is a very useful parameter and a very useful wave in that it's propagating horizontally and therefore is very sensitive to vertical discontinuities. We're very excited about these results so far for actually using ground roll in more of a migration and scattering set of concepts and processes to create further pictures of the near surface. So we'd like to thank you for your attention. Once again, our apologies for not being able to present in person, but we wanted to make sure that we were able to communicate some of these results, which we're very enthusiastic about. Thank you very much for your attention.